Hello friends, welcome to Mu Lessons. This is the second part of our previous video that is about the basics of field effect transistor. So in the previous video already we have seen the review slides, what we have seen or what we have discussed in the previous video. That was basically on FET, JFET, junction field effect transistor. In this part of this video we will study the basics of this MOSFET, types of MOSFET and how these are made. So this is the circuit symbol for enhancement type or N-channel MOSFET. Now these MOSFETs are similar as the construction of this JFET. You can see this is the metal gate. Some MOSFET means metal oxide semiconductor field effect transistor. So just with the combination of FET, MOS is added. This MOS is metal oxide semiconductor, and this is because of this metal gate oxide which is directly in contact with the gate, so that we can apply the gate voltage to this metal gate. And rest, the substrate body, the source, drain are similar. So for these types of MOSFET, this is a simple biasing circuit. In case of JFET, this part was reverse bias, that is VGS was reverse bias, but in case of MOSFET it is forward bias. Now if VGS is less than VT0, that is the PN junction between the drain and the body in the reverse bias, and ID will be 0 in this case. So VGS should be large. Similarly, if VGS increases much more than VT0, then a channel of N-channel type or an N-type material is induced in the region under the gate, and as this gate potential will increase further, the channel becomes more thicker. For small values of VDS, ID is proportional to VDS, and this device behaves as a resistor whose value depends upon the gate potential, that is VGS. So repeatedly I am saying FET is basically a voltage control device, and this voltage control device is by the gate voltage, the potential which we are applying at this gate potential. This is basically required, or this controls the flow of this drain current across the circuit. Now when this VGS is increased greatly, then there is a channel in part of N channel. The N-type materials is induced in the region under this gate, and there will be a flow of electrons from this drain to source. Now as this VDS increases, the potential on the drain source increases, the channel pinches down and the drain and the ID current more slowly. Finally what we get, if VGS minus VDO is greater than this VDS, then ID current becomes constant at particular region, and that is known as the saturation current. This is also similar to that we have seen in JFET case. Now for this enhancement type MOSFET, there is a control current voltage relationship diagram. So the locus of the point, it lies at this point. This point, particularly what we call the locus of the point, divides the two regions, that is the triad region and the saturation region. In case of the saturation region, the current value remains same, and this is basically controlled by the gate voltage VGS. Whenever the VDS, that is the voltage across the drain source, is greater than VGS minus VT, or the threshold voltage, then it comes into the saturation region, and whenever this VDS is less than VGS minus VT, then it falls in the triad region. This is a plot of drain characteristics. You can see how VDS changes, or the value of ID also changes. It reaches the saturation level, and this is mainly controlled by VGS. In case of JFET, we are applying negative VGS, reverse bias, but in case of MOSFET we are applying positive side because it is E-MOSFET, enhancement type MOSFET. We have to first enhance the channel or open up the channel, then we can utilize this channel for the flow of electrons. So these types of circuits can be used to plot the drain characteristics. These are some simple circuits basically on the MOSFET. This is our circuit symbol for MOSFET, enhancement type MOSFET. Here is a channel showing some blockades, so it is used for the MOSFET type. These are some more applications about how to diode protects the oxide layers of the destruction by static electric charges. These are some of the pictures of sample NMOS amplifier circuit and the characteristics with the load line diagram. The intersection between this load line and the characteristics gives the Q point. This is the operating point, basic operating point in which this MOSFET can work very accurately or properly without any damage for longer time. So we need to learn all these drain characteristics. As just a basic for this video, I am just going overview. In our main videos regarding the FETs and MOSFET, we will describe it later on. So this is another type of biasing in case of MOSFET, that is known as fixed plus self bias circuit. These are the self bias circuits. These are some circuit diagrams. Now in this case there is no gate voltage is applied. Now in order to enhance this MOSFET we need to apply some gate voltage. So this is a gate bias circuit which is replaced by the Thevenin equivalent. This R1 and R2 is replaced by the Thevenin equivalent RG, and this RG is a parallel combination of R1 and R2, that is R1 into R2 by R1 plus R2, that is equals to RG, and similarly VG is the VTH. So there are several diagrams, graphs, applications of how you can use these MOSFETs. These MOSFETs are also used as low current devices. The more nearly horizontal line results in the less change in the Q point, and that is what we required in our electronic systems. That means whenever there is less change in the Q point, that means it is not so unstable, it is very stable, and that stable conditions are regularly used by the electrons in the electronic systems. Now this was about the small signal analysis or the small signal equivalent of the FETs. This is the open circuit VGS, gate source voltage, which is applied. This is the transconductance GM into VGS. This is a voltage source, and this VGS is responsible for the flow of ID current from drain to source. So these are some diagrams of FET small signal equivalent circuit, and that accounts for the dependence of ID and VDS. So the analysis of these types of circuit will give some plots of graphs, and that is very much important for the analysis of the variation of ID with respect to VDS. These characteristics are also used for the calculation of GM, that is the transconductance, and the RD, that is the resistance, diode resistance. These MOSFETs, like the previously JFETs, can also be used as an amplifier. This is one of the sample diagram or the circuit diagram of common source amplifier using MOSFET. So these are just basic ideas about this. There are a lot of things to learn in case of MOSFET FETs. There are thousands of circuit diagrams. So these are just main applications for just beginners. Now for drawing an AC equivalent circuit of an amplifier, assume all the capacitors C1, C2, Cs as short circuited elements. That means these R2 made short circuited, and short circuit the DC supply also. Then replace the FET by a small signal model. If you are very much aware or very much acquainted with the small signal analysis, you can easily make it. Then you have to replace this FET by its small signal model. And after that you will get the AC equivalent circuit of such common source amplifiers. So once again I want to review it. First we need to assume all the capacitors to be short circuited, C1, C2, Cs, all the capacitors short circuited. We need to short circuit the DC supply also, then replace the FET part with the small signal model. and we'll get the CS amplifier. Now this part also applies for the MOSFET case also. You can draw these things for the MOSFET also. This is for FET, example has been given for FET. You can draw such diagrams for MOSFET also. In this case, the gains AV will be V0 by VGS, and this V output will be I0 into RL, or minus GM VGS into RL. GM is the transconductance value. So the voltage gain AV is given as V0 by VGS, which is equals to minus GM RL, and this RL is the parallel connection of small RD with this RD. The input impedance, if you see from this side, from left to right, then input impedance is just a parallel connection of R1 and R2, and output impedance is the parallel connections of RD and small RD. So this analysis of CS amplifier with respect to, or on basis of this potential divider bias or the voltage divider bias, can also be done by using the small signal analysis. So there are many applications of this MOSFET JFET timed amplifier circuit using this MOSFET. This is a circuit diagram of common source amplifier using the MOSFET, unlike like we have used in JFET also. Then also in this case also we need to draw the small signal equivalent. We have to follow the same procedure as we have followed in the JFET part. There are some output diagrams. So in this way you can learn many things about MOSFET and all, and in our next video we will go in brief or in the internal side of how this happens. So this is just a comparison of JFET, depletion MOSFET and enhancement MOSFET. The main thing is about the pinch off voltage. In case of JFET it is negative, in case of depletion layer also, depletion MOSFET is negative, but in case of enhancement type it is positive. It rises from the positive x-axis, you can see from this graph. And these are just the basic circuit diagrams in order to remember how this how can you recognize this JFET, MOSFET, depletion MOSFET, E-MOSFET whenever you find these types of circuit diagrams. These are basically for N channel devices except for the direction of the arrowheads. In case of P channel you just need to change the sides. You can find these are the P channels circuit symbols. Thank you.